Good morning to everyone. Today we are going to see about unit number 2, transmission characteristics of an optical fiber in optical fiber communication EC 875. Our first topic is signal degradation in optical fiber. In the first unit we have to know about that how the optical signals are converted into, it means electrical signals are converted into optical signal, and optical signal is received, it means that electrical signal is received by the receiver. By what way we have to completely understand. And in our unit number 2 we have to find out the any distortions are there, or distortions will completed in our optical fiber communication. Signal degradation, topic is in signal degradation in optical fiber. The signal is transmitting through the optical fiber in degraded into mechanism. One is an attenuation and one more is an dispersion. Here the both are important to determine the transmission characteristics of a fiber in an operating wavelength. What is an attenuation? We know that some of the signals are lost while traveling or while communicating to one place to another. The most important characteristics of a cable is power loss in an optical fiber cable. This power loss is called as an attenuation, is also known as signal losses. The power loss in the fiber cable is defined by the ratio of the input transmitted and optical power Pi into an optical output power P0 from the fiber is described by number of decibels. It means that A, which is equal to 10 log of Pi divided by P0. Here we can represent the attenuation in terms of dB. Alpha dB L in L, which is equal to 10 into log 10 of Pi divided by P0, where alpha dB is an attenuation, signal attenuation, and L is an fiber length. Next we have to see about the basic attenuation mechanism. Basic attenuation mechanisms in a fiber are: one is an absorption, and second one is in scattering, third one is in radiative losses of the optical energy. Next, absorption is related to the fiber material and scattering are due to the fiber material and the structural imperfection in the optical fiber waveguide. And radiative losses occurs whenever an optical fiber undergoes the bend. It means that both macroscopic and microscopic bend of a finite radius of curvature. First we have to see about the absorption losses. Absorption loss is related to the material composition and the fabrication process of the fiber. Absorption is caused by three different mechanisms. One is an absorption by atomic defects in the glass composition, eccentric absorption by impurity atoms in the glass material, intrinsic absorption by the basic constituent atoms of the fiber material. Absorption by atomic defect or imperfections or atomic structure in the fiber material. Let us consider the example: missing of molecules in the atom, high density of clusters of atom groups, axis and defect in the glass structure. Absorption losses arising from these defects are negligible compared with the intrinsic and impurity absorption. Next one is the intrinsic absorption. Intrinsic absorption is associated with the fiber material. Suppose we can consider a pure silicon dioxide, it is an intrinsic absorption. Electronic absorption bands in ultraviolet region and atomic vibration band in the near infrared region. Other type of absorption, one is an electronic absorption EA, occurs when the photon interacts with an electron in a valence band and excites it to a higher energy level. The electronic absorption is associated with the band gap of the material. The UV edge of EA follow the empirical formula alpha UV, which is equal to C into E power E by E0. Second one, ultraviolet absorption decays exponentially with an increasing wavelength and it's small compared to the scattering loss in the near infrared region. UV losses we can represent it as alpha UV, which is equal to 154.2 into x divided by 46.x plus 60 into 10 power minus 12, exponential value of 4.63 divided by lambda. Next is an eccentric absorption. Here this absorption is due to the impurities in the fiber material. One is an transition materials metal impurities, and one more is an OH ions in the atoms. Transition metal impurities, it is an iron, cobalt, chromium, copper, nickel, lead metal impurities. In ultra loss fibers from vapor oxidation deposition method, impurities level ranges from 1 to 10 parts per million. The transition metal ions produce losses from 1 to 10 dB per kilometer. This effect metallic impurities can be reduced by class defining technique. OH water impurity ions. The OH impurity results from the hydrogen flame used for hydrolysis reaction. It means that silicon chloride and germanium chloride and potassium chloride. Next one is in scattering method. Due to a non-uniformities in the fiber optic cable, the straight line path of the light rays gets deviated. It is referred to as scattering. In the case of optical fiber cable, some of the optical power is propagating one mode to the another mode. The transferring takes place through the leaky mode or radiation mode. These leaky mode, it create scattering losses. This type of loss is caused by the interaction of light with the density fluctuations. Here most of the fibers we have a density variations. The type of density, the intensity variations in the optical fiber, the scattering will occur. Basically, the glass is composed randomly connected a network of molecules which made up of several oxides and increase the composition fluctuations. In the case of multi-mode fiber, there is a higher dopant concentration and greater composition fluctuations. This is have more scattering losses. We have variety of scattering losses. One is a linear scattering and non-linear scattering. Further, the linear scattering is classified into Rayleigh scattering and Mie scattering, and non-linear scattering is further divided into two methods. One is an stimulator Bernoulli scattering, and one more is an stimulator Raman scattering. We know that linear scattering is nothing but an power is transferred from one mode to another mode in all ways, but there is no change in the frequency on the scattering. There are two types of linear scattering. One is the Rayleigh scattering and one more is the Mie scattering. In Rayleigh scattering, the sun is scattered in the atmosphere to the sky color blue. This scattering takes place in all directions. The Rayleigh scattering coefficient is denoted by gamma r equal to 8 pi power 3 divided by 3 into lambda power 4 n power 8 p squared beta c t f into k. And one more is an Mie scattering. This variety of scattering is in hologenetic, which are comparable with the size in the guided wavelength are called Mie scattering. This is one of the linear scattering, which always in forward direction. Factors are responsible for a Mie scattering. One is in cylindrical structure of cable is not in perfect manner, and imperfections of core and cladding interface. Core and cladding refractive index is not uniform. Through an optical fiber, there are more fluctuations in the core diameter due to bubble and strain of the fiber. One more is a non-linear scattering. Here we classify into stimulated Bernoulli and stimulated Raman. Here stimulated Bernoulli means the laser light beam is traveling in an optical fiber. There are variations in an electric field of this beam. This is an Bernoulli scattering, and the stimulator scattering is nothing but an inelastic scattering of photons. This is what our Raman scattering. And one more is in bending losses. Here there is an abrupt change in the radius of curvature is called as an bending losses. One is in macro bending and micro bending. Macro means the bending diameter is in large, the macroscopic bending will occur. The bending losses is in small, the micro bending losses is there. Thank you.